One day, at another time, a girl will unearth the civilization that has been buried deep for so long. See you on that day.
Tadi uji itunya di mana? Uji apa? Masuk.
Halo, Dr. Umeeda.
Hello.
Hello, yeah.
Hello.
Yeah, thank you very much for accepting our invitation to give talk.
Yeah, you are welcome. So may I test the sharing my screen?
Yeah, we are, I think we will start soon, but okay.
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 Can you see my screen?
Yeah, we can see your screen.
Okay.
So before you start, I will give some introduction.
Oh, thank you. Thank you.
Yeah. Oke, selamat siang Bapak Ibu sekalian. Terima kasih atas kehadirannya pada Kolokium Fisika Kuantum BRIN. Kolokium ini rutin akan diselenggarakan setiap 2 pekan sekali pada pukul 13.30 sampai 15 WIB dengan menghadirkan pembicara dari internal pusat Fisika Kuantum BRIN maupun pembicara tamu dari luar BRIN. Topik yang disajikan sangat beragam dari fisika partikel hingga fisika material dan mencakup juga penelitian-penelitian fisika terkini yang dibahas secara ilmiah populer. So I will switch to English. Good afternoon everyone. Thank you for coming to our physics colloquium. And today we will have Dr. Hiroyuki Umeeda from Chinese Center of Advanced Science and Technology. So before we start, I will read his short CV. So Dr. Hiroyuki Umeeda is was graduated from pure Hiroshima University from bachelor degree to doctoral degree. So from 2012 to 2017. So for academic career, he was postdoc in several places in Hiroshima University, in Shimane University, also in China, Academia Sinica, Institute of Physics, from 2018 and until 2022. And now from 2022 until now, he's postdoc at China Center of Advanced Science and Technology, Institute of Higher Energy Physics, Chinese Academic of Science. So, so your talk time, it's about 1 hour, Dr. Umeeda, and after that it's followed by question. So you may start now, please. Yeah.
Okay. Thank you so much for the introduction. I'm Hiroyuki Umeeda, and first I'd like to thank for organizer to have me as a speaker. And I am postdoc, and I've been working on the theoretical side of the particle physics, especially the processes where the bottom and charm Quarks decays are involved. And to my understanding, the various study topics of quantum field researchers are here, so, and including high energy physics. So I try to do my best to make my talk slide as comprehensive as possible. Okay, first I'd like to start from the introductory part of this talk. As it is known, most of the experimental observed data can be explained by the standard model of particle physics, which is given by this type of particle contents. And for matter field, it includes quarks and leptons, and the interaction between those particles are given by the force mediator that is referred to as gauge bosons. For example, for W and Z boson are responsible for weak interaction, and gluon is for strong interaction, etc. And in addition, there's a Higgs boson that is responsible for generating particle masses through Higgs mechanism. And if we have a look at the detail of quark sector, it includes up and down quarks that forms the usual bound state of barium, such as the proton and neutron. And in addition, there's also meson state. For example, this is pion state that consists of up and anti-down quark. And actually, there's not only up and down quark, but also other kinds of species of quark flavors that is referred to as a flavor of particles. And those are actually in the experiment. This type of three types of generation structure has been observed, as well as the lepton sector. And only the difference between those particle species come from their masses. For example, if we for the case of charm or bottom quarks, those masses are much heavier than the ordinary up and down quark. And for the case of lepton, it is similarly the electron mass is much lighter than the tau lepton, but the other types of interaction property are basically identical. And if we consider charm quark, one can get another types of bound state of barium. For example, if we replace the up quark inside the proton by charm quark, one can get another bound state of lambda C barium state. And similarly, by replacing a quark inside a pion, it can get D-meson state. And similarly, for the case of bottom quarks, there's lambda B barium and B-meson state. And actually, those heavy types of hadrons are given by unstable particles, where those lifetime is typically given by 1 picosecond. So after the experimental production of those particles, it immediately decays into other lighter particles, such as pion or leptons, etc. And actually, there's some kind of experimental investigation that creates those heavy meson baryons that is referred to as the flavor factory experiments. And the example is given by Bell experiment, where the quite huge amount of B-meson pair is created, and its amount is typically 1 billion, so that it enables one particular precise measurement of this sector, heavy Cox sector. And research objectives for such flavor factory experiments are twofold. The first one is the test of the standard model, especially weak and strong interaction that every quarks undergo. And another objective is search for beyond the standard model. And actually, there's several motivations to extend those particle contents, where the detail is given in the next slide. And there are multiple motivations to consider beyond the standard model, but in this slide, only partial examples are listed. And the first motivation is that the presence of dark matter that is firmly indicated in the astrophysical cosmological observations. And for the case of in the standard model, it doesn't contain the candidate of the dark matter as the neutrino cannot be. And so in this sense, the extension of the standard model motivated to explain dark matter. And another motivation is the neutrinos are somehow extraordinary light particle than the lighter particle than other ones. And so there may be underlying theoretical mechanism to explain the lightness neutrino, such as a seesaw mechanism, where the heavy right-handed neutrino is introduced in addition to standard model particles. And another issue is that there's a matter and antimatter symmetry issue. And actually, for antimatter, there are antiproton, antineutron, and positron, etc. And those particles are on the similar footing as the usual matter, except that the antimatter has a positive charge to usual particles. However, due to the cosmological observation, the amount of antimatter is known to be fewer than the fewer number compared to the ordinary matter. And this kind of phenomenon is not explained within the standard model, so that again the explanation of the standard model is motivated. And another question is whether or not proton decay occurs or not. And actually, this process is generically predicted by the grand unified theories, where it gives a unified description of the mentioned 3 interactions in the previous slide. So this gives it some typical beyond the standard model scenario. And in view of those motivation, there are several experimental searches for beyond the standard model. And the first direction of such experimental investigation is given by a high energy frontier, where the beam energy is taken to be so high to get heavier new physics particles. And the recent example such experiment is the LHC experiment in CERN for ultra-length CMS experiments, and that is able to investigate the Higgs sector within and beyond the standard model. And also the dark matter is also searched if given that it couples with the standard model particles. And there's another direction referred to as a high intensity frontier, where the collision beam is taken to be so intense to enable precise measurement. And the example that I already mentioned is B and charm factory experiments, and also tau lepton is produced. And the examples are Baba in SLAC and Bell2 in KK and Bessel in IHEB. And there's another type of observable referred to as a muon anomalous magnetic moment. And for this observable, it has been known that there's a long-standing problem where the standard model prediction is in contradiction with the experimental data. And the recent experimental investigation has been done in the ephemeral muon-G-3 experiment. And there's another type of observable referred to as the neutron electric dipole moment that is again sensitive to the new physics contributions through the time reversal violation effect. And the experiment, this is a partial sample experiment that is conducted in Paul Scherer Institute and Triumph in Canada. And for the case of proton decay, there's an underground experiment in Super Kamiokande. And there's also a neutrino physics, such as diapay, Dune, Nova, and T2K experiment. And for the case of B and charm factory experiment, the corresponding theoretical analysis is challenging due to the uncertainties in strong interaction, where the details is given in the next slide. And for strong interaction, the theoretical analysis is given by quantum chromodynamics, where the classical level Lagrangian is given by this expression that is based on SU3 gauge symmetry. And this theory is characterized by its non-perturbative phenomena. And the example of such a kind of phenomenon is given by confinement. And due to this phenomenon, and quark and gluons are not observed in usual experiments. And instead, what is actually observed is only baryon and meson states. And underlying theoretical mechanism is still unclear. While in the past, there's some theoretical proposal based on the superconductivity picture, where it is assumed that the QCD vacuum is occupied by the QCD monopole state. And in that case, as in a similar way as a type 2 superconductivity picture, where the Cooper pair condensates, and due to the similarity to this superconductivity, there's a due to the monopole, the QQ bar between the QQ bar pair, the flux tube is formed that leads to the linear potential between quarks that leads to confinement. However, whether or not the monopole is really condensed in the vacuum is a non-trivial issue, and only the limited cases such kind of monopole condensate is demonstrated, such as extended supersymmetry for Yamil theory, known as the cyber-grid theory. And actually, this confinement issue is intimately related to the millennium problem for Yamil theory and mass gap, and still this is still non-trivial. And there's another non-perturbative phenomenon in QCD, referred to as the chiral symmetry breaking. And in this issue, the proton, usually proton masses were known to be around 1,000 MeV, but actually, if we interpreted that those proton mass consist of three quarks that forms it, its mass is those quark masses. Some of those three quark masses is merely 10 MeV or so. That is much below the proton masses. So in order to properly interpret the proton mass, the quark masses are dynamically generated by QCD interaction itself, in particular the instant effect, that is a classical solution in the Yamil theory. And actually, before such kind of chiral symmetry breaking, there's original symmetry that prohibits quark mass, so that the quarks up and down quark are approximately massless. But this U3 symmetry is spontaneously broken by the QCD interaction, due to quantum effect. And after that, such kind of spontaneous symmetry breaking, there's a large constituent quark mass of inside the proton is possible, so that generates the physical mass. So this chiral symmetry breaking is non-trivial as well as the confinement phenomenon. And so one may wonder that whether or not beyond the standard model research is possible or not in the quark sector, because in QCD there's some uncertainty at first glance. And actually, there are several approaches for new physics search in quark sector. First one is given by lattice QCD, where the space-time of the theory is discretized to enable the numerical evaluation path integral, including quantum effect, based on first principle approach. And another types of method is given by analytical ways by means of the small parameter expansions. And the first kind of such kind of expansion is given by chiral perturbation theory, where this is taken as a expansion parameter, where this lambda chi SB is a chiral symmetry breaking that is generated by QCD itself. And this is energy of the typical energy of the process. And so if you consider low energy process that is much smaller than this one, one can take this as a expansion parameter to predict observable. And actually, there's another type of expansion that adopts opposite inverse of this typically inverse of this quantity based on the heavy mass expansion of quarks, such as bottom quark. And actually, typically the bottom quark mass is around 5 GeV or so. So QCD's scale is typically 300 MeV. So this is quite small number to be can be expanded. That is referred to as a heavy quark expansion. And by means of this kinds of method, even theoretical, even precise calculation is possible for specific observable for quark sector process. Next, in this slide, some details about the weak interaction is given, where the corresponding theory is given by the Weinberg-Saraf theory, where the corresponding gauge interaction is given by Cu2 cross U1 that corresponds to the unification of electroweak interaction. And due to the Higgs mechanism, it is spontaneously broken by the ordinary electromagnetism gauge group. And in that case, the Higgs is condensated in Q electroweak vacuum. That for that case, then the W boson acquires typically its heavy mass around 100 GeV scale. And if we consider a neutron beta decay, its corresponding diagram is given by this one. Here, the W boson propagate mediate weak force here, and due to the quite heavy aspect of W boson mass, the propagation length of W boson is typically short distance. So one can contract this short line into the point here, and in that case, one can obtain the effective field theory for this Fermi interaction here. And for the case of B-meson decay, similar kinds of discussion is doable by replacing down quark decay into up and lepton process here by the bottom quark decay into charm quark here. And again, this propagation range of W boson is short distance, so it can integrate up to get the effective field theory for Fermi interaction. So effective field theory offers a useful methodology in analyzing low energy phenomena, and particularly the observables in B and charm quark decays, etc., can be calculated by effective field theory for both for within and beyond the standard model. And as an advantage to consider B factory experiment, that the experiment can test symmetry relating particle and antiparticle, and this is a state of B0 bar method that includes bottom quark and D bar quark. And if we interchange the charge and parity transformation property, one can get another state of B-meson that includes B bar and down quark, and those are particle and antiparticle to each other. And a non-trivial point for this transformation is that whether on CP symmetry is violated or not in the experiment. And in order to test this, it is possible to consider B0 decay into J psi K short. And J psi is a state that consists of charm and anti-charm quark pair. As this K short is a state includes the Strange quark. And it is also possible to consider another decay process where the initial B meson is replaced by B bar. And if CP symmetry is preserved, the event number of this first process is equal to the second process. And this is an experimental result in Babar. And this this solid line corresponds to the initial B0 decay, and this dashed line is B0 bar decay. And as one can see from this figure, the event number shape is different for these two cases. So CP symmetry is violated for B-meson, this B-meson decay. And such kind of CP violation is consistent with Kabibov-Kobayashi-Masaka theory in the standard model. And this is a CKM matrix that represents the transition strength of W boson interaction. And this is a experimental constraint on Kabibov-Kobayashi-Masaka element, and in particular, the horizontal and vertical axis correspond to the parameter that represent the entry of CKM matrix. And these colored regions correspond to the various types of experimental constraints, and that includes the Cham-Quark decay and also bottom Quark decay. And for the case of K-on, the CP violation constraint is included, and for bottom Quark, B-meson decay into up Quark and some leptons decay is also included. And as one can see from this figure, the various experimental constraints are simultaneously satisfied by the particular choice of theory standard model parameter. So it leads to some successful aspect in the standard model. And in this figure's constraint, it includes the observable in KK1 mixing and BB1 mixing. Those are referred to as the neutral meson mixing processes, where the detail is given in the later slide. There's another advantage to consider B-meson or Cham processes. It is for rare decays to search for beyond the standard model. And in the case of the standard model, some of the meson decays referred to as flavor changing neutral current process are known to be suppressed. And such kind of rare decays include K-long to mu bar, and B-meson decays XS gamma, etc. And actually, actually those processes are prohibited by the classical level and occurs only at the quantum level. That is known as the Grashow-Ilopoulos-Mariani mechanism. And due to this, this K-on decay into mu occurs only at the higher order in weak interaction here, and also the bottom Quark decay into strange radiative decay occurs only at the loop level. And actually, those processes are advantageous in BSM searches, since the corresponding standard mode background events are typically fewer than ordinary processes, so that new physics contribution may be emphasized. And in a similar way as the strange and bottom Quark case, one can also consider the Cham-Quark rare decays. And actually, for the case of Cham rare decays, the typical pattern of processes different from K-on and bottom Quark case. And actually, for Cham, the GIM suppression works more strongly, and the rare decay is even rarer. And actually, this point leads to difficulties in both theory and the experimental side, because for the theoretical study, if there is a cancellation that occurs in the theoretical observable, in that case, the even tiny error, the Q3 calculation may be emphasized after such a cancellation that leads to some difficulty in the analysis precision. And for the case of experimental, it's again difficult because the rare decays event number is fewer, so it needs large number of statistics. So next, I'd like to move to the theoretical analysis for bottom Cham-Quark decays especially the lifetime analysis for B and D-meson. And those lifetimes are defined simply by taking simply as an object that is inversely proportional to total width. Sorry, this is lifetime is one of the primary observable for testing the standard model as well as beyond the standard model. And the experimental data for lifetimes are precise, that is of 0.1% uncertainty. This is a heavy flavor averaging group data for B-meson lifetimes. And for the theoretical method to analyze the lifetime is based on the heavy Quark expansion that I already mentioned. And here the 1 over MB is taken as the expansion parameter. And by if we use this method, the total width is represented by this formula, where the leading term starts from unity up to overall constant. And the remaining terms correspond to the higher order correction that is by heavy bottom Quark mass. And for this theoretical method, some theoretical assumption is made that is referred to as a Quark-hadron duality. That is where the detail is again given later. And for the theoretical side, the precision is limited, especially by QCD uncertainties, and the errors are at most about 20% for total width and 2% for lifetime ratio. Next, I'd like to in the next slide, I'd like to give the detail about this formula of total width. It's given here, and by means of 1 over MQ expansion. And this MQ is either bottom Quark or charm Quark, and if we take charm Quark, one can calculate the D-meson width as well as bottom Quark B-meson case. And actually, this leading term corresponds, this first term corresponds to the leading order effect, and the other terms are suppressed by quadratically or cubically by heavy Quark mass. And those higher order correction vanishes for infinitely heavy Quark mass. And so in that case, this total width is approximated only by the first term here. And the corresponding diagram is given by this one, where the bottom Quark inside the B-meson weakly decay into some fermion pair. And if we take the on-shell cut of this process due to optical theory, we can get the total width. And in this diagram, this spectator Quark that forms the bound state together with bottom Quark does not join the interaction because only the bottom Quark weakly decays. And so it indicates that this leading order term does not depend on the species of spectator. So it indicates that the lifetimes are common for B plus and B sub D and B sub S meson, because only the difference between them is spectator Quark. And for example, for charged B meson, it's up Quark is and B sub D for down Quark, etc. And similarly, if we consider D meson, the D0, D plus, D sub S lifetimes are common. But this is a caveat is that this is a case where the charm Quark mass is infinitely heavy. So in reality, there's a correction, higher order power correction that is not negligible. And there's another type. One can also define alternative observable, alternative to the total width. And there's this is a lifetime ratio. This is, for example, B plus lifetime divided by B sub D lifetime. And as I mentioned, those B plus and B sub D lifetime is common. So this at the leading order, we consider leading order correction, this lifetime ratio is unity. And sub-leading terms are represented as a remaining expression. So if this lifetime ratio data is close to 1, in that case, the heavy Quark expansion is more likely to be convergent. So in this slide, the comparison between theory and experiment for lifetime ratios listed. The first line is the first result is B-meson case. This is second one is second one is charmed meson case. This is these are for only for baryon case for beauty and charmed baryon case. And this line is heavy Quark expansion result based on theories. And this line is the heavy flavor averaging group result. And here the theory detail. And this theoretical result is based on these three papers. And and from this table, one can find that for B hadrons, the lifetime ratios are always close to unity. And experimental data consistently reproduced by the heavy Quark expansion. So it indicating that 1/MB expansion successfully works, and no implications of duality violations are seen. But for the case of charmed hadrons, the situation is different, and some lifetime ratios show large deviation from unity, such as the D plus over D0 lifetime case. Its value is significantly deviate from unity, indicating that large power correction. And also the tensions are found for some lifetime ratios of baryons. This is xi C and omega C baryon case listed here and here. So there's a subtle point in applicability of heavy Quark expansion to charmed hadrons case. So as shown in the previous lifetime case, there is a difficulty in treating charmed Quark, and actually charmed Quark mass is some kind of unique scale. Its mass value is 1.3 to 1.7 GeV, and this mass scale this mass scale is too heavy for applying chiral perturbation theory. But as indicated in the previous slide, it may be too light for lambda QCD over MC expansion. So then the charm analysis is theoretically challenging. And in particular, there's some difficulty in D-diva mixing. Where the detail is given in the next slide. And for this process, the strong suppression exists due to the GIM mechanism. And heavy Quark expansion is not successful, and experimental data not quantitatively reproduced yet. And in this work, we consider the possibility that this type of situation D-diva mixing may be the indication violation of Quark-hadron duality. So in this slide, some details about neutral meson mixing is given. And in this phenomenon, if we produce B0 state in the experiment, it may transit to the B0 bar state due to time evolution. And so B0, typically after 6 picoseconds, B0 transit to B0 bar and again go back to B0 alternately. And this kind of process is possible due to weak interaction given by this box diagram for B0 mixing, and this is D-diva mixing. And actually, this time revolution of this process can be given by the Schrödinger equation, a coupled Schrödinger equation of this form. And first line corresponds to D0 state evolution, and second line B0 bar, and it mixes with the mass matrix here. And actually, this evolution of the system can be diagonalized by introducing mass ident state for D-meson, where this remains doesn't mix after the time due to time evolution. It remains the same state. And one can define the observable for this process. Here, there's X is proportional to the mass difference between those ident state, while the Y is for the redox difference for these two types of mass ident state. And the CP, we consider CP conserving limit those are related to the off-diagonal element of mass matrix. And both xn normalized by total results so that they are defined to be dimensionless. So next, I'd like to move to the theoretical side of theoretical analysis side of DDBA mixing. Actually, it has been known that there are two methods to analyze DDBA mixing. First one is the exclusive method, and the second one is the inclusive method. For the case of the exclusive side, the theoretical analysis is taken as a theoretical analysis is taken as a hedronic level, while the inclusive side is Quark level computation is adopted. For the case of exclusive side, the theoretical calculation hedronic decay such as d/pi or d/kk are hard to calculate. So instead of theoretically predicting those hadronic processes, experimental data are used. Meanwhile, for the case of inclusive side, it doesn't rely on experimental data. It's given by purely theoretical method to analyze DDBA mixing. And for the inclusive case, Quark-hadron duality is assumed. Next, in the next few slides, I'd like to next few slides details about both exclusive and inclusive case are given. As for the former case, for the exclusive approaches, this y related to width difference is given by this expression in the CP conservative limit. Here, this gamma plus and gamma minus CP idenstate decay width of D-meson. And because this is something related to width, one can represent it in terms of this type of expression, where the sum is taken by all possible hadronic final state that the D-meson can decay into. And it can also written by this type of expression that is explicitly given by hedronic matrix element to the effective Hamiltonian, weighted by phase space functions. And if you consider particular final state contribution for PP mode, this PP is a pseudoscalar meson state. And the partial contribution to this Y is given by this expression. It includes D-meson decay into pi or pi eta or kk, etc. And it includes the k-pi contribution that is also sensitive to the strong phase difference between this k-pi state. And in order to determine those strong phase and branching ratios, the experimental data is used to determine this contribution. So based on this exclusive method, there are several previous works. And actually, this is experimental data for Y from a heavy flavor group. And the first group has conducted the analysis of topological approach. In this case, the result lead to the PP contribution is 0.086. That is much percent. It's multiple the 0.6% in the experiment. And for the case of PB final state contribution, where this B is a vector meson state, there are two solutions corresponding to the fitting analysis minimum. But both of the two solutions gives a smaller value than the experimental data. And the second group considered the factorization assisted topological approach, and where the lead to PP, VV, PV, and VV modes are taken into account. But the VV mode is shown to be negligible. And by taking summing over this PP and PV mode, the result is given by this number, the 0.2%, that is again below the data. So these kinds of results indicate that the other two-body or multi-body final states contributions are necessary to take it into account. To summarize, for the exclusive analysis, half value of data is explainable. So there's another approach to calculate DDBA mixing from inclusive approach. For that case, the Quark level analysis is adopted, and the corresponding diagram is given by this box diagram. And again, due to the short range propagation of W bosons, we can get full Fermi interaction by means of effective operator analysis. And as an equation, if we write this amplitude as box diagram amplitude as a A12, it consists of two types of contribution. First one is the M12 that corresponds to off-shell intermediate Quarks contribution, and the other one is gamma12 for on-shell intermediate states. And by applying the heavy Quark expansion, this gamma12 is written by this type of formula, where this Cn is a Wilson coefficient that corresponds to the weak interaction matrix effect that originates from the W boson propagation effect here. And this is a matrix element corresponding to the operator that induces full Fermi interaction. And here's the Quark mass appears as a suppression factor. So it indicates that if Quark mass is heavy enough, this expansion is more likely to be convergent. So for the inclusive analysis, there are several contributions. The first one is the two down Quarks are in the loop of box diagram. But there are other types of flavor contribution, like D-meson S-bar is intermediate, also for S and D bar, and SS is also possible. And in addition to those diagrams, there's additional contribution coming from bottom Quark in the loop, but those bottom Quark loop contribution is CKM suppressed. So if we take some certain approximation, it can be negligible. And if we further assume that the strange Quark mass is equals to down Quark mass, one can write this sum of this diagram contribution as this type of expression, where this lambda is defined as a product of CK matrix element here. And actually, in the standard model, those CKM elements are given by a unitary matrix that satisfy this expression. And but now we adopt the approximation where bottom Quark related CKM is negligibly small. So in that case, the last term is neglected. And if we use this approximate unitarity relation, one can find that this summation over these three diagrams vanishes. So it indicates that the total D-bar mixing is suppressed by the GIM mechanism. And in this expression, we assume two approximations. First one is bottom Quark CKM is negligibly small, and the second one is strange Quark mass is equal to down Quark mass. And so if we take account non-zero, if we take account those deviation between strange and down Quark mass or non-zero CKM bottom Quark mass, bottom Quark effect, we can get a non-zero contributions to the D-bar mixing. So D-bar mixing observable is sensitive to the SU3 breaking effect that is typically given by the strange and down Quark mass difference, or it may be proportional to small CKM factor lambda b that is suppressed by small capybara parameter. So in this slide, theory and experimental result comparison is given, where the theory side is given by the inclusive analysis. This left one is for D-bar mixing, and middle one is B sub S, and the right one is B sub D mixing. The first line is standard model result, and second line is experimental result. And from this table, one can find that for B sub S and B sub D mesons, the experimental data are reproduced within the experimental error for B sub D mixing with those difference, that is still consistent to be 0. And for the case of D-bar mixing, the situation is different. And for this case, order of magnitude is not reproduced within the naive leading power analysis. And actually, as I mentioned, the standard model result for X and Y are strongly suppressed by the GIM cancellation mechanism in the standard model, and the value of X and Y are typically 10 to minus 7. But the experimental data typically 10 to minus 3. So there's four orders of magnitude disagreement. So for this issue, there are several possibilities discussed in the literature. The first one is a violation of Quark-hadron duality. And in this paper, suggests that the 20% violation of duality explains the data based on a simple phenomenological model of duality violation. And another possibility is that contribution of higher power suppressed terms are not negligible. That is originally suggested by Georgi. And actually, this type of direction gives a source of essentially breaking that is linear in strange Quark mass that may avoid the severe GIM cancellation mechanism. And this paper show that in that case, X and Y are order of magnitude of X and Y are consistent with data. And this next paper investigated that with some assumption about the hadronic matrix element, X and Y can be as large as 10 to minus 3. And there's another investigation based on the renormalization scale settings. For this research direction, if the scales at which the bilocal previous box diagram process is calculated are taken as if the scale of those calculations are taken as different values for individual Quark contribution, like DD bar case and SS bar case. If we distinguish the scale between each diagram, there may be sufficient enhancement that is realized after taking some of those possible flavor contributions that is discussed in this paper. And another possibility may be the beyond the standard model. And in this work, we consider the first possibility of violation of Quark-hadron duality. So in this slide, details about the Quark-hadron duality is given. This is an example for E plus minus 2 hadrons. And here the E plus minus electromagnetically annihilated into Q-giver pair. Corresponding, but this is Quark, but experimentally, what is the experimental observed hadrons, especially meson state, and the experimental observable is E plus minus 2 pi pi and 3 pi and 4 pi, etc. And if Quark-hadron duality is realized, this E plus minus 2 Q bar cross section is equals to sum of these exclusive cross sections, like summation over 2 pi, 3 pi, etc. And if this inclusive cross section is not equals to sum of exclusive cross section, it gives one definition of duality violation. And similarly, there's another process of B decay into XCL new, etc. This XC is a state that includes all possible charmed state. For that case, the theoretical analysis is given by this diagram, where that is analogous to beta decay, and the corresponding hadronic states are B-meson decay into DL nu or D star L nu. This D star is a spin one state of D-meson, and there is this B-meson decay into multi-body hadronic state like D pi, etc. And again, if Quark-hadron duality is realized, this sum of these process cross section is equals to this Quark level process. And one non-trivial point in this issue is that whether or not the Quark-hadron duality is possible. Actually, in these regards, there's these regards, it should be noted that ultimate accuracy of the heavy Quark expansion analysis is limited due to some kinds of factorial divergence in perturbation theories. And actually, such kind of factorial divergence includes several examples. The first one is proliferation of Feynman diagrams. And so for this case, if we consider one loop quantum collection, the number of Feynman diagrams is maybe only a few, but if we consider two loop, the number of diagrams start to increase. And if we consider 5 loop, the number of diagrams may be more than 10,000 or so. And if we consider n loop diagram, the number of diagrams is typically characterized by factorial of n. And if we take n goes to infinity, typically divergent. And another such kind of factorial divergence is given by Rinomaron that is characterized particularly by the bubble chain diagrams that also gives rise to factorial divergence. And there's another issue, presumably the least famous one, but there's another factorial divergence coming from power corrections that correspond to the factorial divergence for the 1 over MB power correction. Because this B-meson decay is infinitely relying on this expansion. If there is a factorial divergence, there is uncertainty in the theoretical prediction for inclusive side. So in the previous work, there are several approaches to study the violation of Quark-hadron duality. In this slide, those previous works are listed, and each method has an advantage and disadvantage. So the first one is the resonance-based model, and for this method, the largen limit and the linear edge trajectory are considered as a starting point of discussion. And the advantage is that the theoretical prediction in some sense rigorous because it sometimes relies on the solvable aspect of theory, but it has an disadvantage that it is mostly a toy model of QCD, because sometimes it relies on the two-dimensional theory, and in that case, how the result is changed from the two-dimension to four-dimension, there's a non-trivial aspect. And another study is from the instanton-based model. And for this case, this method takes account of a fixed-sized background instanton that is more or less as an orientational direction to capture contribution that is related to the factorial divergence in power corrections. And the advantage is that some realistic contribution could be examined, and this is not a toy model. And the disadvantage that the detail of the QC vacuum is involved in a non-trivial way, so that in order to perform the precise analysis, the details about QC vacuum is necessary. And another recent approach is made by lattice QCD. And for this case, the reconstruction of the spectral function is considered for inclusive B-meson decays. And the advantage is that it is based on ab initio evaluation of hadronic correlator, while it's a disadvantage. There could be disadvantage in this theory that specific duality violating components are suppressed in the Euclid space, because the lattice QCD analysis mostly relies on the Euclid space. And in this slide, concrete method to investigate the duality violation in this work is given. So actually, in order to study whether or not the inclusive rate is equals to sum of exclusive rate is satisfied or not, we consider space theory based on space-time dimension d equals to 2 instead of usual d equals to 4. Actually, there's an advantage to consider two-dimension, and that is summarized in this table. And for the case of inclusive analysis, the heavy Quark expansion analysis, the theoretical calculation is similar for both d equals to 2 and 4, so that left-handed side of this expression is can be determined in a quite similar way. However, for the case of exclusive side, there are several differences. And if we consider experimental determination of exclusive widths, it is possible for 4 dimensions by properly conduct an experiment, but for 2 dimensions, that is not practical. And for the case of theoretical determination of right-handed side, the situation is again different. And for the case of 4 dimension, in order to calculate exclusive sum, we need to evaluate each type of meson decay, like d to pi pi, d to kk, and each process it requires quite non-trivial calculation of QCD. So it is difficult to do it in the 4 dimension. But for the case of 2 dimension, there's an advantage for the theory side. Actually, QCD is solvable in the large n limit. And actually, such kind of 2-dimensional large n QCD, that is referred to as the Tohout model, possesses a major nature of ordinary 4-dimensional QCD, such as asymptotic freedom and confinement that is built in for the case of a 2-dimensional theory. And actually, as I mentioned, the heavy Quark expansion is in common with the 4-dimensional case. But there's several different points, such as the gluon is not a dynamical particle, and the phase space function is different from 4 dimensions sometimes, and 2-dimensional phase space often has a singularity in 2 dimensions. But due to the quite similar aspects of heavy Quark expansion, the Quark-hadron duality violation is qualitatively testable within this model. And there are several previous works for investigation Quark-hadron duality based on Tohout model. And those are already applied by non-leptonic decays and also semi-leptonic decays, and particular high order correction to non-leptonic decays, and also the differential semi-leptonic widths. And in this work, we consider that we study the heavy meson mixings, such as D-bar or B-bar mixings. And the difference between mixing and the previous decays is that the D-bar mixing is suppressed by the GIM mechanism. So in that sense, as I already mentioned, the tiny duality violation is possibly enlarged after the cancellation. And we also study the lifetime ratios, and actually power interference numerically analyzed within the leading decay contribution. Duality is tested in such a way that both the CKM allowed and suppressed contribution are included. So in the Tohout model, the bound state equation for mesons can be solved. And actually, this is given as a Bethe-Salpeter equation that is responsible for bound state, relativistic bound state problem that is given in the right congage. And as a diagrammatical equation, it's given by this one here. This is a meson state that is connected to the Quark propagator. And this is a bound state should satisfy this relation. And it leads the Tohout equation of this form. This is the equation version of this one. And it constrains the meson mass squared and light-cone wave function of meson in this way. Here, this is this beta is a QCD coupling of certain kind of unit given by this one, and this beta is scaled like a constant in the large n limit. And by solving this bound state equation, one can determine masses and wave functions for mesons within the formalism. And as a numerical method to solve the Tohout equation, we consider BSW improved Markov technique, where the meson wave function is expanded as a series of sign function, and each of coefficient can be determined in such a way to solve this Tohout equation. And if you use this basis, this Tohout equation is represented as eigenvalue problem. So it can be solved in the standard way through some numerical implementation. And in the Tohout model, the D-bar mixing is represented as an exclusive process in this type of expression. This is a width difference in D-bar mixing. In the CP conservation limit, its expression is given by exclusive sum over possible intermediate state. And this T corresponds to the color allowed tree diagram. It's given by this one here. The charm Quark inside the D-meson weakly decays, and it decays into the meson state M, and M is either pion or kaon. or its excited states. And this small m and small k are labels for radial excitation. And if we take k equals 0 and m equals 0, it corresponds to the ground state contribution. And and here the sum is taken over all possible intermediate states that the D-meson can decay into. And this factor corresponds to the phase space function in 2 dimensions. And actually, for the case of expression of color tree amplitude, its analytical expression is given by Greenstein-Levitt a long time ago, and its formula is given by this one. Here, this capital C, D, and F overlap integrals or wave functions that can be determined by solving the Q3. And in this slide, the analytical check of Quark-hadron duality is investigated to study whether or not duality is violated or not. We introduce a notation of generalized weak vertex of this form. Here, this G2 is a weak gauge coupling, and this is a relevant CKM element, and it is multiplied by tensor structure here, and this CV is and CA normalization of vector current and actual vector current, and then for the standard model case, it corresponds to the 1/2 and -1/2. But we keep this CV and CA as a free parameter, and by means of this notation, one can write an inclusive width difference of this expression by calculating the box diagram here. And there are 2 types of contribution. First one is actual vector contribution. The second one is pseudo-scalar contribution. And each term's coefficient is given by CA and CP, and the analytical expressions are given here. Here, this includes the phase space function F, G, and H here. And if we take the heavy-Quark limit, only the leading term comes from F, and the F's expression is given by this one. It also includes the for Fermi interaction matrix element of this one and this one. And usually it requires the non-perturbative analysis in QCT, but within the Largen approximation we adopt, this can be factorized into this expression that is represented by represented only by the meson decay constant and meson masses. And for the case of pseudo-scalar, this R is given by the object of this relation. And if we further take the down Quark massless limit, down Quark appears as an intermediate state. This gamma 1,2 is reduced to the simple form as this one. And this is an inclusive result from Quark level calculation. And in the next slide, we compare this with exclusive result. For the case of exclusive width difference, this is an exclusive expression that corresponds to sum over all possible hadronic states, and the corresponding diagram is given by this one, where the pion exclusively appears instead of quarks. And actually, the right side of this diagram is related to the left due to time reversal. So that here we only focus on the left side of this diagram. And if we have a look at this part surrounded by a red circle, this circle part is given by this one. And because this in this diagram, the Quark lines are connected to the weak interaction vertex, and it's given meson state, so it's proportional to decay constant times momentum, and the decay constant definition is given by this one. That is represented by wave function of intermediate pion state. And for the expression of pion wave function, there are several properties from Tohoft equation. And actually, if we consider massless limit of up and down quarks for pion, one can find that the ground state pion wave function is equals to unity due to the solution of the Tohoft equation. And for the case of excited states, it is possible to use the completeness of Tohoft wave function that corresponds to this equation. And actually, if we use relation, what can show that all the decay constant for excited state of this pion state should vanish for any kinds of radial excitation. And only the non-zero contribution arises from the ground state contribution. So actually, due to the proportionality to decay constant, here only the non-zero contribution arises from a ground state contribution in this diagram. So all possible sum of intermediate state is reduced only to the ground state contribution here. And in that case, this expression is reduced to this formula that is again represented by the pion wave function. But again, we can use the property of ground state pion wave function that is equals to unity. And finally, it reduced to this type of formula. And actually, this formula agrees with the previous inclusive result. So in that case, for the massless case of up and down Quark, the Quark-hadron duality is realized analytically. And that is a analogy of the Pauli interference contribution that it was discussing long time ago. Next, I'd like to move on to the numerical results for D-D-bar mixing. And first, I'd like to show the result for individual flavor contributions, such as intermediate state is only taken as the SS bar state, and we compare this with the corresponding exclusive state corresponding to K-on and K bar. And next, I will also show the result of sum over flavors case that is subject to the GIM cancellation mechanism corresponding to sum over these three types of diagram, and we compare it with corresponding exclusive rate. And for the case of second one, the order of magnitude is non-trivial under the variation of strange Quark mass because it's sensitive to SU3 breaking. This is the first result for individual flavor. This is for this plot, the horizontal axis is charm Quark mass normalized by Q3 coupling. The vertical one is a width difference in D-D-bar mixing. And this horizontal black line corresponds to the inclusive result for one strange Quark and one down Quark, and the corresponding exclusive process of K-on and pi-on intermediate states is given by red point. And from this figure, one can find that the inclusive and exclusive results are different for small charm Quark mass, but if we take charm Quark mass to be heavy, those inclusive and exclusive results agree with each other eventually. And there's another result corresponding this green dashed line, where that corresponds to the two strange Quark as an intermediate state, and corresponding hadronic result given by blue points includes two K-ons. Again, in this case, the small charm Quark case, the inclusive and exclusive results are different, but if we take heavy charm Quark mass, it eventually agrees. And this type of tendency is consistent with widely recognized tendency in the literature. Next, I will finally talk about the sum over flavor case for GIM cancellation mechanism. And before showing a numerical result, in this slide, some details about the phase space function is given. This is an inclusive calculation result that I already showed. And for the phase space function, the detail phase space function for F and G and H is those details expressions are given by this one. And here it's represented as Z, and Z is defined by this one. That is the ratio of light Quark mass divided by charm Quark mass. And And actually, from those expressions, this F is a phase space function that also appear in the four-dimensional analysis, while F and G does not appear in the for usual four-dimensional analysis, and it's referred to as 2D specific phase space. And for F, it's called the 4D-like phase space. And we present the result for two cases. First one is the case where the only 4D-like phase space is included in this expression. And another result is pure two-dimensional result. All of the phase space functions are included. So this is a result in the presence of GI mechanism. This horizontal axis strange-Quark mass divided by fifth decoupling, and vertical one is the exclusive width difference normalized by inclusive width difference. And this black point is 4D-like phase space result, and this cross is all phase space inclusion result. And this dashed line corresponds to the MS bar mass of strange-Quark in 4 dimensions. Charm-Quark mass is fixed to the MS bar mass in 4 dimensions. And from this figure, one can find that if the strange-Quark mass is a bit smaller than the MS bar mass region around this region, one can find that the ratio of exclusive and inclusive width difference is larger than 10 to minus 3, 10 to 3 for the case of 4D-like phase space function case. This tendency is consistent with what is indicated in the 4-dimensional experiment, where the inclusive and exclusive result, there's a 4 orders of magnitude discrepancy for heavy Quark expansion data. So in this slide, there's also the result for B bar mixing. Left one is B sub D, and the right one is B sub S. And again, the Charm-Quark mass is varied, and horizontal one is exclusive width difference normalized by inclusive one. But this typical scale is order of unity, unlike the previous plots for charm mixing. And from those results, in the region where the Charm-Quark mass is smaller than the pole mass corresponds to this line or this line. And for B sub D mixing, the correction to the inclusive rate is up to 40% around here, maximally 40. So the correction of this size is not excluded yet. The experimental data for B sub D width difference normalized by B sub D width is still consistent with 0 for the experimental side in 4 dimensions. And for the case of B sub S mixing, the correction to the inclusive rate is up to 18% here. And this result is still consistent with what is currently indicated in 4 dimensions. And actually, the ratio of heavy flavor range data to heavy Quark expansion in 4 dimensions gives this numeric. It's very close to 1 within error, and 18% correction is not within 1 sigma, but well within 2 sigma. So I'd like to summarize. There are some non-perturbative aspect in QCD, and it gives rise to the obstacle within the standard model, as well as the new physics searches. And charm decays and mixing is generically difficult than one for bottom Quark processes, and thereby requires refined theoretical investigations. And Quark-hadron duality is a central hypothesis which would works for beauty hadron lifetimes, although it is inherently hard to quantify. And we have studied Quark-hadron duality for neutral meson mixing on the basis of the Tohoft model, and we obtained this result. Thank you. I'm running out of time. Thank you for your.
Okay, thank you very much to Dr. Umeeda for the nice presentation. So I will give time to participant if you have other question? Please. Any other question from participant? Okay, maybe I have a naive question, Umeeda-san.
Yeah.
Can you go to maybe page, sorry, slide 11 or something?
This one?
Not, sorry, I don't remember. Previous. Okay, that one. The just no, next one.
Next one. This one?
Yeah. So here, if you take the MT goes to infinite, how about the in the how to say in the common factor you have here also?
Common
So
factor. You mean this one?
no, MK power 5. So how you treat that when you take the MK, it goes to infinite?
Sorry, which one? This one.
Yep.
This one behaves also like infinity, but so this leading order term is fifth power of overall behaves like fifth power of heavy Quark mass. So it this is leading order. In that sense, leading order term is also infinity, but the relative size between leading order term and next term is different. So in that sense, leading order term is dominant in the heavy Quark limit. It is suppressed by 2 powers of heavy Quark mass in the heavy Quark limit.
Okay, maybe can you remind us why we have to take the heavy Quark mass limit goes to infinity?
For example, it's actually bottom Quark mass is not infinity but very heavy. So actually this power collection is very small, and it's if you consider heavy Quark mass is very heavy, so it's convenient to organize some interpretation. For example, the B plus lifetime is equals to B sub D lifetime if those high order fraction are all negligible. So in that case, the B plus divided by B sub D lifetime is very close to 1 because the other terms are higher order collection corresponding to this one. And actually, experimental data in the next slide shows that this B plus over B sub D lifetime is very close to 1. It's 1.08 or something. So it means that those power collection is very small compared to the leading order term. So in that sense, considering the heavy Quark limit, may be convenient to organize some interpretation about this expression.
Okay, I see. Okay, from the participant, if you have question, is there any question from participant? There is one question from the chat. I will read.
Okay.
You mentioned about the experiment at BB bar. It reminded me about the BB bar and Bele, which I heard in one conference when I was an undergraduate student. In that time, I really wish I could visit BB bar and Bele, but unfortunately, I never had a chance. Could you tell us those two facilities? Maybe,
Okay.
yeah. This,
Yeah, actually, I'm working on theoretical side only to, as long as I know, actually, Baba experiment has been already terminated, and now Bell has been already updated to Bell 2 experiment, and this experiment is still ongoing, and no, there's a updated plan of Baba has been once planned in Italy, but unfortunately it was not realized. Actually, for facilities, I'm not an experimentalist, so I don't have much detail, but yeah.
okay. Okay, we hope it's answer your question, Muzaki. Yeah. Is there
you're
any
welcome.
other question? There is one question. Does this type of work help to improve uncertainty for delta ACP? I think ACP asymmetry maybe.
CP asymmetry for D-meson decay into pi and KK. Yeah, actually, if you mean it's a CP asymmetry in B to pi KK decay, it's this kind of study is sort of independent study. So in order to get the detail of D-meson exclusive decay, there's another kinds of effort is necessary. For example, D-meson may couple to the intermediate resonance state like F1790 state, and there's some kind of theoretical proposal that if D-meson couples such as hadronic resonance state, the D-meson CP exclusive CP violation is enhanced, so that the CP violation in D-meson may be consistent with the standard model prediction. But such kind of detailed hedronic resonance topic may not be the same as a DD mixing.
Okay. So, okay, yeah. It's answer, I think, yeah, from a question, Mr. Renat Primolando. So, is there any other question from the participant? Okay, can you tell, there is one question. Can you tell me what is the beta parameter in x-axis plot you show in the end of the slide? Is it related to the wave function?
Actually, beta is a QCD coupling constant, and actually in this study we consider two-dimensional gauge theory, and for that case, gauge coupling has a mass dimension unlike the usual 4-dimension. So this beta is mass dimension 1, and actually this there's some different point from usual 4-dimensional gauge theory, because the QCD originally has a mass scale as a coupling constant, and this combination is taken as a dimensionless combination.
Mm-hmm. Here in the vertical axis also dimensionless? gamma ij.
Okay. This width has a dimension 1, but sorry, I didn't explain that. It's given in the unit of this one. The
Okay, it's scaled by that factor.
Yeah.
Okay. Okay, yeah. So thank you. The question is fun. Any other question? Or from Ahmad Jafar Arifi, could you explain a bit more about tough model and light cone gauge?
Previous pages. Okay, it's two-dimensional theory, and actually asymptotic freedom is the same as a usual four-dimensional theory, and confinement actually if we it's this Tohoft equation gives a mass spectrum of mesons, and due to mathematical aspect of this equation, one can find that meson mass is always larger than the Quark masses, and there's no tachyon. And it means that free Quark does not appear as a mass spectrum. So in that sense, the confinement is built in. And okay. And this can be used as a research of heavy Quark expansion, because the inclusive side is very same, but the exclusive side is very useful to take some over all possible excited state contribution that can be very easily done for the case of light cone gauge expression of this one. This can be numerically solvable, and in the case of axial gauge, it's this equation is more non-trivial. And if we consider axial gauge, the chiral symmetry breaking can be discussed in a more non-trivial way. But here in the current work, we consider light cone gauge, where the solving QCD equation is more straightforward.
So to solve that equation only with the numerical method, or we can use ansat, for example, to solve that equation?
We solve it numerically. Analytical, as long as I know, there's no analytical solution. Is very exists only some limited case. Here in this work, we consider some practical value of charm Quark mass, strange Quark mass, etc. So for such kind of particular choice of masses, there's some difficulty to get the analytical solution. So in this work, we use the numerical solution.
Okay, I see. Okay, from the participant, if is there any question to our speaker? Okay, so we are running of time. So thank you, Umeeda-san, for talk to our physics colloquium. Thank you very much. We really appreciate. Okay, I think we will end soon this physics colloquium. Terima kasih kepada seluruh peserta kolloquium yang selalu antusias setiap pekannya menghadiri kolloquium fisika ini. Kolloquium ini tentunya tidak akan bisa terlaksana tanpa partisipasi aktif Bapak Ibu sekalian. Ikuti terus kolloquium fisika quantum brain dan nantikan informasinya di sekitar beberapa hari sebelum kolloquium di halaman Facebook Pusat Riset Fisika Kuantum ataupun Instagram dengan nama akun Quantum Research ID. Sampai jumpa di kolokium berikutnya. Tetap semangat, selamat beristirahat sore dan melanjutkan aktivitas. Demikian saya akan end meeting for all saat ini. Bye-bye. Thank you, Umeeda-san.
Yeah, welcome.
Thank you very much. Thank you for all participants.